Okay, all right. We're going to go over the free response that we made up to go along with this homemade ballistics pendulum testing in Mr. Ross's engineering physics class that we found on Twitter. I'm going to play the video for you real quick so you get an idea of what we're talking about here. Fire a ball bearing into a styrofoam ball. Styrofoam ball acts like a pendulum, swings up to a measured height. And you can see it rotates around there, and the ball bearing falls out. It's perfect rotation, so we get to see what really happened. Now, let's take a look at what we decided to do with this and what the math ends up looking like. So, data from the video and from Mr. Ross replying to me on Twitter entails this is a ballistics pendulum, is what we call it in physics. We use this to figure out how fast ballistics things fire, like launchers and guns. It involves conservation of energy and conservation of momentum because it does involve an inelastic collision and a pendulum then acting. And so then what we measure from the video is we measure a change in h, a change in height of 0.2 meters, 20 centimeters. You can see that with the meter stick that's in the shot. That's going to unlock a gravitational potential energy as the H in the MGH. Then we have the masses from Mr. Ross. He says that I'm going to call MS the mass of the styrofoam ball. I'm going to call MB the mass of the bearing. And those are both equal at 16 grams, which is going to translate to 0.016 kilograms. And when they combine and move as one in the pendulum motion, I'll call it MBS, the mass of the bearing and the styrofoam ball, combining 0.16 to 0.032 kilograms. My three questions I'm going to ask with this free response. Part A, I'm going to ask, what is the kinetic energy of MBS just after the collision, just before it really begins its swing? So basically the kinetic energy of the pendulum at the bottom of the swing. Then we're going to convert that into momentum of the pendulum just after the collision. And then we're going to use the law of conservation of momentum to find out what was the VI, the initial velocity of just the ball bearing right after it was fired from the gun. That would be its velocity just before it impacted the styrofoam ball. All right, getting into part A, we're going to unlock that kinetic energy. I like to use what we call the guess method. So you see GUESS in gray down my work. And for those of you who aren't aware of that, that is G for given information, U for unknown, what we're trying to find. E is for the equations that we may use. The first S is for substituting into the equations, and the last S is for solving for your unknown. It gives you a nice way to work through your work. So our givens are the change in height and the mass of the bearing and styrofoam ball together. Our unknown is the kinetic energy, which I'm calling KE subscript B, B for bottom of the swing. That J is for joules. And then the equation for kinetic energy is 1/2 mv squared, putting in subscripts for the bottom. And then gravitational potential energy is mgh. And then pendulums follow the law of conservation of mechanical energy. And so I have capital M, capital E for mechanical energy. And we're going to say the mechanical energy at the bottom of the swing will equal the mechanical energy at the top. And so I have B for bottom and T for top there in my statement of the law of conservation of mechanical energy. Now the next thing I'm going to do with that is I'm going to expand that law. I'll drop the equal sign and I will expand it. So here I am dropping the equal sign and then expanding MEB to kinetic energy and gravitational potential energy, and MET to the kinetic energy and gravitational potential energy at those locations. And then I'm going to leave kinetic energy alone as kinetic energy because that's actually what I'm trying to find in my unknown. And I'm going to expand the gravitational potential to MGH, noting that the bottom height we're going to say is height 0 meters. And I'm going to expand kinetic energy at the top just to show you why that kinetic energy will become 0. At the top, we say it stops at the tops. Its velocity will become instantly 0, just instantaneously there at the top of the flight. And expanding GPET to MGH. And we have that H of 0.2 meters at the top of the flight. Okay, now we get to get rid of things. So this whole gravitational potential energy turns into 0. And the kinetic energy just keeps on dropping down. The kinetic energy at the top turns into 0. And we then get to say that when we multiply the mass of the bearing and the styrofoam ball together with I'm using 10 meters per second squared for g and 0.2 meters for the maximum height we reach, we're going to get 0.064 joules of gravitational potential energy that came from 0.064 joules of kinetic energy at the bottom of the swing. And that gives us our answer to part A. All right, now let's take a look at part B. We're going to change that kinetic energy into the momentum so that I can then use the law of conservation of momentum in part C. And so here we go, moving into my work for part B and C. In part B, reapplying the guess method here. We'll go ahead and zoom in on it a little bit. We're going to now have this yellow kinetic energy at the bottom of the swing that I've just found from my work in part A. So I'm carrying that over. And then I now have the mass once again. Now we're going to have the unknown is the lowercase p for momentum. I'm using a BS for my subscripts there for the bearing and the styrofoam ball together. And I'm using a prime. I'm saying that the prime represents the momentum just after the collision, but really before the swing. And momentum units are kilograms times meters per second because the equation is mass times velocity. Okay, the equation for momentum then would be P equals mv. And then another helpful equation is we're going to go from kinetic energy into momentum. So I'm going to use the equation for kinetic energy as well. I'm actually going to rearrange this equation to solve for the velocity and find that and then carry that velocity over into momentum. And so that's what I've done here in my next line when I'm starting to substitute. I've got this rearranged so that the velocity of the bearing in the styrofoam ball prime just after the collision is equal to the square root of 2 times the kinetic energy at the bottom divided by mbs. Then substituting in the numbers in my next line here, we're going to then calculate this, and it crunches out really nicely to a nice perfect 2 meters per second. So that is the speed that we have, but it's not the momentum. We have to account for the mass. And so we're going to take that speed, we're going to put it in to the equation for momentum. I'm going to reapply my substitute step and my solve step once again and get the momentum of the BS system of 0.064 kilogram meters per second. And that is the momentum it has right there just after the impact happens. Part C is now going to ask, let's run this further back in time to the very beginning of the event to the speed of the ball bearing before it impacted the styrofoam ball. So we reapply the guess method. Our givens are the mass of the bearing and styrofoam together. We're going to split that now just to look at the mass of the bearing as 0.016 kilograms. We now have our salmon colored momentum of the BS system, which we're going to use as a given in this new situation. And we're looking for the VB in meters per second. I'm calling that the velocity of the bearing as my initial velocity of the bearing before the impact. We're going to look at, since we have momentum, we're going to use the equation for momentum and just applying that for the bearing. So I'm just using B's for the ball bearing. We also can use the law of conservation of momentum, which I'm writing here in symbols. I'm going to say that the momentum before the collision is equal to the momentum after the collision, and I'm just using a P and a P prime to differentiate those. Now we're going to expand it just like we expanded the law of conservation of energy. We're going to expand the law of conservation of momentum. We're going to drop the equal sign, and then we're going to expand the momentum before. We had two objects before that then combined into one object after the collision. And so we're going to have, before the collision, we're going to have the momentum in the bearing and the momentum in the styrofoam ball. And then after, we're going to have the momentum of the bearing and styrofoam as one object. Now then we start to substitute in, so we'll expand the momentum of the bearing into mb times vb, boop, boop, and we'll expand the momentum of the styrofoam ball into ms times 0 because the styrofoam ball was just like hanging there at rest. That's nice because it's going to get rid of this momentum completely, and we're just going to end up with the momentum of the bearing before that. Then all of that momentum is then given to the PBS prime system, in which we already have that momentum from earlier of our 0.064 kilogram meters per second. Divide both sides by MB, and then I'm substituting in here my MB of 0.016 kilograms, and I get my 0.064 kilogram meters per second divided by 0.016 kilograms, and I get a nice clean 4 meters per second. And so it looks like this launcher will fire that little steel ball bearing of 16 grams at 4 meters per second. And yeah, so there we go. We've found the what we call the muzzle velocity of this launcher gun. And thank you for joining me to work out some physics. And again, thank you to Mr. Ross for sharing this video on Twitter and for being so kind as to share the masses with me. All right, that's the science. And you're the physicist, so you keep on physicsing and have an awesome day. Bye-bye.